A few nights ago, astronomy headlines carried an unusual line that sounded almost poetic. An interstellar comet just spoke to Earth for the first time. Not through mathematics or Morse code, not through a blinking light in deep space, but through chemistry, a whisper of molecules that had travelled for millions of years before dissolving for one brief moment under our sun. The report came from a team using the Meerkat radio array in South Africa. 64 gleaming dishes standing silent across the Karoo Desert. At precisely 4:10 in the morning Universal Time, they caught something strange. A pair of tiny dips appeared in the radio spectrum at frequencies around 1665 and 1667 megahertz. To the untrained eye, just another flicker of static. But to those who know the language of light, those twin notes are sacred. They belong to the hydroxyl molecule. Ooh, the child of sunlight and water. And this time the signal wasn't coming from any comet we'd known before. It was coming from 3I/Atlas, a wanderer from beyond our solar system, discovered only months earlier and now gliding toward the sun. The first interstellar object ever to reveal its chemical voice. It wasn't the sound of technology or the cry of an alien transmitter. It was simpler, quieter, and somehow more profound. Water, broken by light, was speaking. And the message, if there was one, was not, "We are here." It was something closer to "I exist." I still remember what warmth feels like. To understand why that matters, imagine what it means to hear water breathing from another star system. Every world we know, from Earth to the moons of Jupiter, carries water as the signature of possibility. But until that October dawn, we had never heard water from beyond our cosmic neighbourhood. Now, for the first time, a molecule formed under a foreign sun had crossed interstellar space, drifted into ours, and responded to our light with a whisper we could detect. The object itself, 3I/Atlas, had been discovered by the Atlas Sky Survey in July 2025. Its path was fast and steep, slicing through the solar system on a trajectory no planet could have given it. That alone marked it as an outsider, a visitor from another sun. By late October, it was nearing its closest pass to the sun, roughly 1.5 times farther than Earth's orbit. But what happened on October 24th, just a few days before its perihelion, was unexpected. The comet's position, barely 4 degrees from the sun's glare, should have made observations impossible. And yet, as sunlight scattered off its warming ice, the perfect geometry of motion created a small gap in the radio noise. For a few quiet hours the universe aligned. Meerkat listened, and the comet answered. The absorption appeared as a soft hollow in the spectrum, the opposite of a burst, a tiny subtraction rather than an addition. Against the radio background it looked like the comet was drinking light, not emitting it. To describe that visually, imagine watching a rainbow reflected on a pond. For an instant, 2 thin colours vanish, absorbed by the water's surface, and in those missing tones, you realise the water is real. That's what happened at 1665 and 1667 megahertz. The missing tone said, "There is water here, and it is alive under sunlight." 2 previous observations on September 20th and 28th had heard nothing. Only this time did the alignment work. A narrow window before the comet rounded the sun and faded again into silence. Later analysis showed the absorption followed the comet's motion perfectly, shifting slightly as it moved, with a width that matched the slow exhale of a vapor cloud, roughly 1 kilometer per second. No instrument fault, no earthly interference, just a pattern born of rotation and warmth. The physics is easy to say but difficult to feel. As sunlight touched its surface, the comet's ice turned to gas, releasing water vapor that broke apart under ultraviolet rays into hydrogen and hydroxyl. Those fragments spun and flipped, each transition leaving a faint mark in the radio sky. It is chemistry at its most poetic. Molecules vibrating in resonance with sunlight, the language of creation itself. To make sense of it in ordinary terms, 3I/Atlas was losing, Every second, something like 1 billion water molecules. That's a number so large it feels abstract, but think of it this way. Every heartbeat of a second, the comet released a mist of ancient water enough to fill a small lake, and each of those droplets, torn apart by light, added its tiny voice to the cosmic hum. Scientists checked, rechecked, and confirmed. The timing matched. The direction matched. The depth of the lines matched what a water-rich comet would produce. What we heard was not static. It was a sigh from another solar system. The beauty of it lies in how ordinary it was. No alien engineering, no coded pulse. Just the physics of ice, sunlight, and time. And yet, within that ordinariness, there's something extraordinary. A connection across light years, carried by one of the most familiar substances in the universe. Every drop of water on Earth, every molecule that moves through your body, vibrates at those same frequencies. The whisper from 3i/Atlas was, in a sense, the universe speaking in its native tongue. And for once, we were listening in the right direction. When the data came in, some scientists described it as the comet breathing. It's a strange metaphor, but it fits. After perhaps 1,000,000 years drifting in frozen darkness, untouched by any star, this wanderer came close enough to ours to warm, to release a trace of itself, and to be heard. It wasn't sending us a message, but it reminded us that in the quiet workings of chemistry, there are stories of origins, of resilience, of how simple elements can carry memory through time and distance. And that is how the story began, not with the roar of a signal, but with the faintest inhalation of light, a murmur at the edge of noise, a foreign molecule awakening under our sun. The universe, it seems, had decided to whisper. And for the first time, humanity had the patience and the silence to listen. In the heart of the Karoo Desert, far from city lights and the restless hum of civilization, the Meerkat Array stands like a metallic forest, 64 giant dishes, pale and still beneath an ocean of stars. The air there is so dry and silent that you can hear the crunch of sand beneath your shoes from meters away. It is one of the quietest places on Earth, chosen for that very reason, to listen to the faintest voices in the universe. On the night of October 24th, 2025, those dishes turned toward a patch of sky dangerously close to the sun. Most radio telescopes avoid such alignments. The sun's interference can drown out even the brightest signals. But on that night, geometry conspired in favour of curiosity. The interstellar object known as 3i/Atlas, then little more than a tiny smear of light on most optical images, was gliding just beyond the solar glare. The timing was risky, the window narrow, but the team had tried twice before and found only silence. They had one last chance before the comet disappeared around the sun. At 4:10 in the morning, universal time, the universe exhaled. A small dip appeared on the readout, so faint that at first it looked like a calibration error. The signal repeated at a slightly higher frequency, a twin echo separated by a hair's width of the dial. Those numbers, 1665 and 1667 MHz, were familiar. They belong to the hydroxyl molecule, the simplest fragment left behind when sunlight breaks apart water. The frequencies were not just close, they were perfect, aligning exactly where theory said they should be. To describe this in a way that doesn't require a spectrogram, imagine two musical notes played on an instrument that no human can hear. They are separated by a barely perceptible interval, like a harmony between two atoms rather than two strings. For decades, astronomers have known that comets in our solar system hum these same twin notes when their ice begins to melt in sunlight. But this time, the source wasn't from within our planetary family. It was from beyond, drifting in from another star system. The scientists froze, staring at the monitors as the data confirmed what seemed impossible. There was no sign of interference. The line followed the comet's predicted motion through the sky. Even as the Earth rotated and the angle shifted, the pattern held steady, moving in perfect step with the traveller. What they were hearing was not a glitch of human machines, but the chemistry of alien ice responding to warmth. Later, one researcher described it not as a detection, but as an encounter. It was as though the comet took one breath, she said, and we happened to hear it. To appreciate how delicate that breath was, picture a glacier waking after 1,000,000 years of sleep. As sunlight touches its surface, molecules of water begin to shake loose, floating away as vapour. In the near vacuum of space, those molecules drift outward, and ultraviolet light from the sun tears some of them apart into fragments, hydrogen atoms and hydroxyl groups. Each of those fragments spins and vibrates in tiny magnetic patterns, creating two characteristic radio tones. They are not emitted loudly, but by absence, by absorbing specific wavelengths from the surrounding cosmic background. In a sense, the comet doesn't sing, it listens, and in its listening it leaves a signature behind. What Meerkat saw was that faint act of listening written into the fabric of light. Two missing frequencies, like small spaces between heartbeats. The width of those spaces told another story. The vapour cloud was expanding slowly, about 1 kilometre per second, an invisible wind of molecules rushing away from the surface. For something so remote, that level of detail is extraordinary. It means that even from millions of kilometres away, we can measure how gently a piece of alien ice melts. The object itself was barely the size of a modest mountain, its path cutting through the inner solar system on a sharp sunward arc. It would reach its closest point, its perihelion, 5 days later, at roughly 1.5 times Earth's distance from the Sun. At that moment, its surface temperature would reach about -40 degrees Celsius, cold by human measure, but warm enough for ice to turn directly into gas. In that fragile balance, the comet breathed, and for a few hours we heard the whisper of its exhalation. If one could translate that whisper into human terms, it might sound like this: "I've travelled the dark between stars for longer than your species has known fire. I have seen no sunlight, no warmth, only the slow drifting of atoms, and now, for the first time, I feel the heat of a new star. I turn to vapour, and in doing so, I speak." No one truly expected such clarity. The odds of the geometry aligning, of the comet's signal escaping the solar noise, were almost negligible. Yet coincidence, or perhaps inevitability, brought it into range. It is tempting to wonder if this moment says something about us too, about how, after decades of searching for messages from beyond, humanity's first interstellar conversation turned out not to be a code or beacon, but a molecule saying what molecules always say when they warm: "I am water and I am moving." For scientists, that was enough. The discovery confirmed that water ice, the foundation of so many cosmic stories, survives interstellar travel. It proved that not. All interstellar visitors are dry rocks like Oumuamua, the first one we ever saw. Some still carry the essential ingredients of life, frozen through the long dark. The realization brought a kind of quiet joy, a recognition that even across unimaginable distances, the chemistry that builds oceans, clouds, and cells is the same everywhere. The numbers, softened into words, tell their own story. Every second, the comet released roughly 1 billion molecules of water into space. Each molecule split under sunlight, forming hydroxyl that hummed at those two frequencies we heard. Those sounds travelled across millions of kilometres to our antennas. It's hard not to feel humbled by the precision of nature's mathematics, unwritten, unspoken, yet unfailingly eloquent. After the detection, the team stayed on alert for confirmation from other observatories. Some data from SWIFT, observing in ultraviolet, matched perfectly. The same water loss rate, the same pattern of activation near the sun. The correlation between light and radio, the two different kinds of listening, was exact. Together, they painted a picture of a world that was not just moving through space, but participating in it, reacting, resonating, leaving traces of its chemistry as a message written in vapor. As the observation session ended, the scientists saved their data, the screens dimmed, and the Karoo Desert returned to its natural silence. Above them, 3I/Atlas continued along its arc, soon to swing around the sun and fade into the depths beyond Jupiter's orbit. The signal was gone, but its meaning lingered. Somewhere out there, between the stars, are countless other wanderers carrying the same frozen breath of water. If one has found its way here, others surely will. The universe, it seems, does not communicate through grand gestures or deliberate designs. It speaks through the quiet repetition of physics, the way hydrogen bonds with oxygen, the way sunlight touches ice, the way silence can become a sentence when someone learns how to listen. That night, in the stillness of the desert, Earth became the ear of the cosmos, and what it heard was not alien speech, but a reminder of belonging, the voice of a molecule older than language, older than planets, older than thought itself, finally heard again, after a journey that began in another sun's light. When scientists looked at the Meerkat data the next morning, they didn't see noise. They saw something astonishingly delicate. 2 perfect notches in the spectrum side by side like the faint indentation of a pulse. Each one told the same story in a slightly different voice. One spoke at 1665 megahertz, the other at 1667. Together, they were not just numbers, they were music. A duet composed by molecules drifting through sunlight. These frequencies belong to the hydroxyl radical, or simply OH, a tiny chemical fragment made when light touches water. It is one of the simplest children of chemistry, but also one of its most expressive. On Earth, we find OH in the shimmer of flames, in the auroras dancing at the poles, in the upper atmosphere where sunlight splits vapor apart. But on that October morning, we were hearing it not from our sky, not even from our system, but from ice that was born under another sun. Explaining what those frequencies mean doesn't require equations. Imagine a tuning fork struck gently in a quiet room. It vibrates with a single, pure tone. Now imagine another fork vibrating at nearly the same pitch, so close that their waves almost overlap. The 2 tones rise and fall in a slow interference pattern, producing a subtle, wave-like beat. That is what happens inside an OH molecule. Its atoms twist and wobble between 2 closely spaced energy states, separated by an interval so small that only radio light can reveal it. When the molecule flips between those states, it either absorbs or emits radiation at those twin frequencies. That, in essence, is what Meerkat heard. Trillions upon trillions of tiny tuning forks made of oxygen and hydrogen, vibrating in unison as sunlight struck them. Each molecule by itself is nothing, but together they create a faint yet coherent pattern, the molecular equivalent of a sigh. And because the hydroxyl molecule can only form where water once existed, those 2 faint lines are nature's way of saying, water is here. For the scientists studying the data, this realization was like turning a key in a long locked door. Until that moment, we'd inferred the existence of water in interstellar objects from their behavior, how their brightness changed, how jets of vapor affected their path. But now, for the first time, we had heard water directly. Not a reflection, not a guess, but an actual chemical fingerprint, caught in the act of reacting with sunlight. To grasp the significance of that, think of what it takes for water to survive between the stars. Space is not kind to molecules. Ultraviolet radiation tears them apart. Cosmic rays bombard them for millions of years. Even gravity can work against them, pulling icy fragments into the depths of cold, dark interstellar clouds where chemistry slows to a crawl. For a piece of water ice to endure such a journey and still respond, still breathe after entering our system, that is resilience at a molecular scale. The observation also told scientists something about the comet's internal structure. From the shape of the spectral line, its width and symmetry, they could infer how fast the gas was expanding. About 1 kilometre per second, they estimated, gentle by cosmic standards. The signal's depth hinted at temperature, around -40 Celsius, or about 230 degrees above absolute zero, warm enough for ice to sublimate, yet cold enough for it to linger. In these conditions, water doesn't boil or melt. It goes straight from solid to vapour, as if the comet were evaporating into thought. The numbers could have been expressed in formulas, but they tell a clearer story in pictures. Imagine a sphere of ice the size of a mountain drifting toward the sun. As light touches its surface, a thin mist of vapour rises. Each droplet lasts only moments before sunlight breaks it apart. The fragments dance, spinning and twisting, emitting those invisible notes that our radio telescopes can hear. The comet becomes, for a brief span of days, a cosmic wind chime, silent to our ears, but echoing clearly across the vacuum. This process, simple yet profound, connects worlds. The same frequencies heard by Meerkat have been recorded from comets like Halley, Hasakutake and Hale-Bopp, all born within our solar system. The hydroxyl molecule doesn't care which star it orbits. Its voice is universal. It hums the same melody everywhere water meets light. That means the chemistry we know, the one that built oceans, clouds, and the molecules of life, is not local to Earth. It is galactic, perhaps even older than galaxies themselves. In that sense, 3I/Atlas became a messenger of something much larger than itself. It told us that the ingredients of life can wander freely between stars, protected in the cold of interstellar space, waiting for a moment of warmth to awaken them. The whisper we heard wasn't about aliens sending messages. It was about the universe itself being fertile, restless, and connected. It is easy to forget that these molecules, though unimaginably small, are the same ones that make up every cell, every drop of rain, every living breath. The water in your bloodstream resonates to the same physics as the water that evaporated from 3I/Atlas. In a way, the signal was not from out there. It was an echo of ourselves, played back across light years. When the scientists overlaid the data from other telescopes, the story grew richer. The Swift satellite, observing in ultraviolet light, confirmed that the comet was losing water at a rate of about 1 billion molecules every second. That number, though vast, is easy to soften. Every heartbeat, a mist of vapour equal to a small lake drifted away from the comet's surface, spreading into space, turning into song. Some might wonder how something so faint could survive amid the sun's noise. The answer lies in the geometry. Because the comet was positioned just a few degrees from the sun, the Doppler effect, the same principle that changes the pitch of an ambulance siren, shifted its signal slightly away from the solar background. The sun's roar moved to one side, and in that narrow gap the whisper became audible. It's like overhearing a single voice in a crowded room, because it happens to be speaking in a key no one else uses, and that alignment lasted only hours. If the timing had been off by even a day, the signal would have been buried in static. The universe doesn't often stage such perfect coincidences. But sometimes, through the combined motion of planets, stars, and human patience, a moment of clarity opens, and through it, knowledge flows. For the public, the story made headlines. For astronomers, it marked the beginning of something new, the dawn of radiochemical astronomy for interstellar visitors. The first time we had listened not for alien words, but for natural ones. It shifted the question from, are we alone, to something quieter and perhaps deeper. How connected are we really? And for those who stayed awake that night at the consoles watching the graph lines move across the screen, it became something personal. they had heard the universe whisper back, not to humanity as a species, but to curiosity itself. A traveller from another star had spoken in the simplest possible language, the language of molecules, and in that simplicity it said everything that needed to be said. The two faint lines, so small they could have been missed, carried an entire philosophy inside them, that existence, wherever it happens, follows the same music. The frequencies may change, the brightness may vary, but the harmony remains, and as long as someone listens, the song continues. Astronomy often appears to be a science of precision, of predictable orbits and clockwork motion. Yet, when it comes to discovery, it's often ruled by coincidence, by the right object drifting into the right alignment at exactly the right moment. The case of 3I/Atlas was one of those rare accidents that felt almost choreographed. Everything about the detection, from the timing to the comet's position in the sky to the sun's background noise, had to align within impossibly narrow limits, and somehow it did. When the Meerkat array pointed its dishes toward 3I/Atlas that morning, the comet's path placed it just 3.7 degrees from the edge of the sun. That's less than the width of your thumb held out at arm's length. Normally, radio astronomers avoid such close approaches. The sun drowns the sky in a roar of static, its surface a storm of charged particles and magnetic fields, each sending out waves that can overwhelm sensitive detectors. Yet in this moment, the geometry worked in humanity's favour. The comet's motion created a slight Doppler shift, a gentle offset in frequency caused by its movement relative to Earth, and that shift nudged the signal just far enough away from the solar background to be heard. Imagine a whisper in a crowded room, nearly lost among hundreds of conversations. You lean closer, not expecting much, and then the speaker happens to lower their voice into a tone that cuts through the noise. You hear a single word clearly, perfectly, before the sound is swallowed again by the crowd. That was the nature of this observation, a precise alignment of motion and light, so brief that it could easily have been missed. Two earlier attempts, made on September 20th and 28th, had found nothing but the hiss of the sun. The comet was still too far away, too cold, its ice is still locked in silence. But as it drew nearer to the sun, warmth began to reach its surface. Temperatures climbed from the deep freeze of interstellar space, hundreds of degrees below zero, to a fragile range where ice no longer stays solid. At roughly -40 Celsius, the molecules began to move. The comet started to breathe, and as it breathed, the vapour created its signature, the faint absorption lines that told us water was stirring. In astronomy, timing is everything. The comet's perihelion, its closest point to the sun, was set for October 29th. The observation on the 24th captured it just before that moment, when its activity was rising but not yet chaotic. Had Meerkat waited another few days, the sun's interference would have been too strong. Had it looked earlier, the comet would have been too cold. What we call a discovery was really a fleeting conversation between ice, sunlight, and luck. Even the movement of Earth played a part. As the planet rotated, the Meerkat dishes tilted slowly westward, tracking the comet across the dawn sky. The curvature of our planet added another subtle effect, a change in the angle of incoming radio waves that helped separate the comet's signal from local interference. The world itself, in its turning, became part of the instrument. The observation wasn't just a human achievement, it was an alignment of the sun, the comet, the Earth, and time. Such coincidences may sound romantic, but they're common in the history of science. The discovery of cosmic background radiation came from a pair of engineers simply trying to remove noise from an antenna. The first pulsar was found by a graduate student noticing an odd blip in a chart recorder. Each of these moments reminds us that the universe sometimes hides its truths in the margins, in signals so faint they appear accidental until someone decides to look closer. 3I/Atlas was another whisper from those margins. The geometry that made the detection possible also revealed something about the comet's path. Most interstellar visitors approach the solar system from random directions, but 3I/Atlas arrived on a near-ecliptic trajectory, the same plane where our planets orbit. That made it an outlier. Statistically, the odds of such alignment are tiny. It is as though, among the endless corridors of space, a traveller from another neighbourhood happened to step directly into the doorway of ours. Some found that coincidence eerie, others saw it as proof that we are finally becoming capable of noticing what was always there. In the early excitement, a few speculations appeared online. Some wondered whether such precision, the near-perfect timing, the symmetry of its twin tails, the faint absorption that seemed to turn on and turn off, could suggest something artificial. Could the comet be a probe manoeuvring itself with jets of vapour to control its path? Could the absorption have been a kind of encoded modulation, a chemical Morse code? These ideas spread quickly, as they always do, because imagination outruns caution. But the data itself told a quieter story. The line shapes, the rates of change, the symmetry, all were entirely consistent with natural cometary behaviour. Beautiful, yes, but not intelligent design. Just physics, performed with the elegance of inevitability. Still, there's a kind of poetry in the coincidence. The same geometry that made the observation possible also made the comet appear to speak. The motion of light and matter conspired to reveal a pattern that seemed almost intentional. It reminds us how perception works, that we too are part of the instrument. When a coincidence feels like choreography, it is because we are watching from the one vantage point that makes it so. The universe is not arranging itself for us, but we are arranged within it in just the right way to notice its rhythm. In the aftermath, astronomers examined the faint tail and anti-tail pattern in the comet's dust. Two streams stretching in opposite directions. It looked symmetrical, almost deliberate, like a pair of wings made of sunlight. The explanation was simple. One tail was formed by gas pushed away by solar wind, while the other, the anti-tail, was a projection effect. Dust particles trailing behind along the orbit, illuminated from our viewpoint to appear reversed. Yet to the human eye, symmetry always invites meaning. We see purpose in balance, intention in repetition. The cosmos, however, achieves beauty without needing a reason. There is a phrase often used in astrophysics. Coincidence is the language of complexity. It means that in a universe governed by countless interactions, rare alignments are inevitable. The miracle is not that this one happened, but that we were prepared to notice it. For centuries, comets were seen as omens, unpredictable, untamable, messengers of change. Now, with instruments like Meerkat, we can see them as they truly are. Archives of chemistry, storytellers of formation, wanderers that carry information rather than prophecy. Still, even with all the data and explanations, there remains an undeniable sense of wonder. To think that a piece of ice, born under another sun, could drift for perhaps 1,000,000 years through darkness, arrive near ours, and in one fleeting alignment let us hear its molecular heartbeat. That's a kind of grace that science alone cannot define. It feels like the universe, in its quiet precision, left a message not in words but in timing. Pay attention. The smallest coincidences hold entire stories. When the observation ended, the Meerkat team saved the raw data, ran calibrations and prepared their report. Outside, dawn began to spill over the desert hills. The array stood motionless, each dish still glinting under the fading stars, as if listening to echoes that only it could hear. Somewhere above that horizon, 3I/Atlas was already slipping into daylight, invisible to human eyes but still glowing faintly in radio. The whisper that had travelled across millions of kilometres was gone, yet the space it left behind was changed. For a moment, the immense machinery of the universe had aligned perfectly. Comet, sun, Earth, and human curiosity, to let a single truth pass through, that beauty and discovery are often the same thing, seen from the right angle. When scientists talk about comets, they often describe them as relics, ancient fragments of the early solar system frozen in time. But interstellar comets are something else entirely. They are not archives of our own history, they are libraries of someone else's. Each grain of their dust, each layer of ice, carries information from a star that is not our sun. To touch them, even with light, is to read a sentence from another world's origin story. For decades, humanity could only guess what those sentences said. But now, after hearing the faint radio breath of 3I/Atlas, astronomers have begun to translate a few words. The comet's whisper confirmed that it contains the same key ingredient found in our oceans: water. But water, simple as it seems, is not just a liquid or an ice. It's a builder. It binds, dissolves, and rearranges molecules. It is, in a very real sense, a memory device. When water freezes, it traps atoms and molecules inside crystalline cages. Each cage holds a record of the environment where it formed, the temperature, the radiation, the chemical neighbours that surrounded it. In that way, every piece of interstellar ice is like a paragraph in a long and ancient text. In laboratories on Earth, scientists try to reconstruct this story. Inside vacuum chambers cooled to near absolute zero, they mix water vapour with small amounts of methanol, ammonia, and carbon monoxide, the raw materials thought to exist in interstellar clouds. They shine ultraviolet light on the frozen mixture, mimicking the weak starlight that filters through space. And after hours or days, when they gently warm the sample, they find traces of new molecules, amino acids such as glycine and alanine, precursors to proteins. No equations are necessary to describe what happens there. It's chemistry unfolding as softly as frost melting on a window. Light provides a tiny push, energy rearranges bonds, and suddenly, lifeless molecules begin forming the alphabet of biology. From these experiments, scientists learned that the universe does not need a planet, or an ocean, or even an atmosphere to begin building the ingredients of life. It only needs time, ice, and light. That is why the detection of hydroxyl, a tiny echo of water breaking under sunlight, matters so deeply. It's proof that even in the emptiness between stars, those same processes are alive. Somewhere, long before the solar system existed, ice like this may have formed in another cloud of gas and dust. Over millions of years, it drifted, collected into a small comet, and was eventually flung away when its native star's gravity shifted. It wandered through the void until, by pure chance, it entered our sky and warmed beneath our sun. And in that moment, its frozen memory was unlocked. The molecules it carried began to move again, and their faint voices reached us through radio waves. When you think about it that way, 3I/Atlas isn't just a visitor, it's a survivor of stellar migration, a physical link between solar systems, a courier carrying microscopic letters written in the alphabet of chemistry. The idea that life's ingredients can travel this way has a name, panspermia, which means seeds everywhere. It's an old hypothesis, but one that modern astronomy has begun to take seriously again. It doesn't claim that life itself floats between stars, but that the ingredients, carbon chains, amino acids, complex organics, are constantly exchanged. Every collision, every comet that escapes a solar system becomes a small act of distribution. Over billions of years, the galaxy functions almost like an ecosystem, trading raw material the way oceans trade currents. The discovery from 3I/Atlas breathed new life into that idea, because if an object can travel so far and still retain ice that can release water that can break into hydroxyl under a new sun, then chemistry truly is universal. The same physics that shaped this comet shaped ours. The same sunlight that woke it also powers our climate, our oceans, our biology. It reminds us that the cosmos is not a collection of separate worlds, but a single, ongoing, experimenting connection. One astronomer described it poetically in a post-observation interview. If you imagine the galaxy as a great body, comets are its bloodstream. They move material from one organ to another, carrying nutrients, carrying memory. 3I/Atlas is a droplet of that blood, and we've just drawn its sample. That metaphor isn't just beautiful, that it's accurate. The detection of water beyond our solar system means that molecular exchange between stars is not rare and not fragile. It means that the elements that make up us, oxygen, carbon, nitrogen, are restless travellers. They've been moving, combining, breaking apart, and recombining long before Earth was born. In that sense, we're made of ancient echoes, assembled from pieces that once belonged to other stars, perhaps even other civilizations that never had the chance to form. There is a kind of quiet humility in realizing this. It turns the question of, are we alone, into something more intricate. Because if the chemistry that builds life is everywhere, then solitude becomes unlikely. It doesn't guarantee neighbours or messages or civilizations, but it guarantees kinship, that everywhere light touches ice, the same story begins to write itself again. When radio telescopes detect the hydroxyl lines, they're not listening to technology. They're eavesdropping on the metabolism of the galaxy itself. Those twin frequencies, 1665 and 1667 megahertz, are like the heartbeat of water. They appear wherever warmth meets frozen molecules. Each detection is another pulse, another sign that matter is still circulating, still alive in its own slow way. You can imagine 3I/Atlas as one small cell in that galactic body, a droplet carrying information. Its travel time may have spanned 1,000,000 years. Along the way, cosmic rays and starlight would have sculpted its surface, darkening it with organic compounds, toughening it for the long voyage. When it finally entered our solar system, it brought with it the residue of those countless interactions, the chemical autobiography of interstellar space. The moment sunlight touched it, that autobiography opened. If we could somehow read those layers of ice like a book, we would find chapters written in starlight. The earliest layers might record the cold birth of its native star. Deeper down, we might find traces of the nebula that once surrounded it, perhaps even signatures of complex molecules born before any planet solidified. Each stratum would represent a different moment in cosmic history, a frozen archive of environments no human will ever see, and yet with a single observation, we can begin to reconstruct some of it. The depth of the absorption line tells us how much water vapour was released. The width of the line tells us how fast that vapour was moving. The temperature inferred from those details matches what ice would experience near 1.5 times Earth's distance from the Sun. With patience and care, data becomes narrative. We can imagine the comet turning slowly, its crust crackling as sunlight warms the frozen plains beneath. Jets of vapour erupt, invisible in space, forming a halo that grows brighter each hour. Each jet releases molecules that catch light, split apart, and sing their quiet tune. For a few days, the entire body becomes an instrument, fragile, ephemeral, and utterly unique. And then it passes on. The sun pulls it forward, it rounds the point of closest approach and begins to fade. Its activity wanes, the signals weaken, and soon it will slip beyond the range of any telescope, heading back toward the cold. But it leaves behind its mark, not only in data but in understanding. For the first time, we have proof that a piece of another star's chemistry can cross into our home and still speak clearly enough for us to listen. When ice becomes a library and light becomes its reader, the universe itself becomes a storyteller. And perhaps the most beautiful part of that story is this: it never repeats exactly. Every comet, every grain of interstellar dust carries a different sentence, but all are written in the same language, the language of water and light. If you think of the Milky Way not as a collection of stars but as a single living system, then comets like 3I/Atlas are its bloodstream. They carry nutrients, the carbon, oxygen, nitrogen, and water that feed the chemistry of worlds. They circulate quietly, connecting one stellar heart to another, crossing gulfs of empty space that to them are simply long, cold arteries. What Meerkat heard on that October morning was one heartbeat of that system, a pulse of chemistry flowing from a distant origin into our corner of the galaxy. Astronomers call it exchange, transfer, or migration, but the idea is simple. Nothing in the universe stays still. Matter moves. Ice evaporates, gas condenses, dust gathers, stars form, planets shatter, and debris drift away. Over time, every element that exists will travel from one environment to another. When a comet releases vapor, it isn't losing itself. It's contributing to the endless circulation of material that keeps the cosmos dynamic. The galaxies we see, spinning in silent spirals, are not static structures but metabolic ones, constantly reshaping and replenishing themselves. The discovery of water in 3I/Atlas reminds us how profound that metabolism is. We tend to think of water as local, as belonging to Earth, or at least to our solar system. But the truth is broader. Water is a migratory molecule. It forms wherever hydrogen and oxygen find each other in cold conditions, often on the surfaces of tiny dust grains that float in interstellar clouds. Those grains, coated in frost, collide and stick together, building up the first solids of new planetary systems. Later, those solids become comets, and some of those comets get flung away by gravity, carrying their icy cargo into deep space. For millions of years they drift, silent messengers between stars, and once in a great while, one of them wanders close enough to another sun, ours for instance, to wake and speak. You can imagine the process as a galactic water cycle, stretched across unimaginable distances and timescales. Clouds condense into stars. Stars create heat and light that evaporate ice. That vapor spreads into space, freezes again on dust, and begins the cycle anew. On Earth, the water that fills our oceans and falls as rain is part of that same continuum. The droplet that slides down your window may once have been frozen in the shadow of another sun. The molecule in your breath may have drifted for eons before finding its way here. Every exhale is, in a small way, a contribution back into that cosmic exchange. The term panspermia captures one part of this idea. The notion that the seeds of life might travel between stars carried by comets or dust grains. But even if we set life aside, there is still a form of continuity that borders on the biological. Atoms move through the galaxy the way blood moves through a body. There are sources and sinks, cycles of creation and decay, patterns of circulation that maintain balance. Some scientists have begun to use the phrase galactic metabolism, not as a metaphor, but as a framework for thinking about how material and energy flow on a cosmic scale. 3I/Atlas is a visible thread in that network. It came from another stellar nursery, perhaps a place richer in carbon or with heavier isotopes of oxygen, subtle differences that record its birthplace. When it passed through our solar system, it shed a little of that foreign chemistry into our environment. A few molecules from its vapor may still linger in the upper atmosphere of Earth, mingled invisibly with ours. In that sense, our planet is no longer made purely of local matter. It contains within its air and oceans traces of other suns. This idea is not new to astrophysics, but it becomes deeply personal when you think about it slowly. The iron in our blood was forged in the core of an ancient star. The calcium in our bones came from the debris of a supernova. The oxygen we breathe was once bound up in rocks, released by time and heat. Now, with interstellar comets like 3I/Atlas, we can see the next step in that story. Not just where elements were born, but how they travel and mingle, how they keep the universe from ever becoming stale. The cosmos, in its immense scale, is surprisingly efficient at recycling. The spectral fingerprints from Meerkat showed that the hydroxyl signal was steady and symmetrical, not distorted by turbulence or irregular jets. That suggested a consistent source, perhaps a smooth layer of surface ice sublimating evenly, rather than sporadic eruptions. The comet was releasing vapor calmly, as though it were exhaling at a measured pace. That steadiness helped scientists estimate its production rate, about 1 billion water molecules per second. It's a number almost too vast to imagine, but softened into imagery, it means this: every second, the comet produced a cloud of vapor roughly the size of a small mountain, spreading outward in a slow, invisible wave. Those molecules, once released, joined the solar wind, a continuous stream of charged particles flowing from the sun. Together they formed a temporary bridge, a narrow conduit through which the material of another star mingled with ours. The bridge lasted only a few days, then dispersed into the heliosphere. But it was enough to make the point clear. The galaxy is not a collection of isolated islands. It is an ocean with currents that mix its waters constantly. We live in a cosmic archipelago where every shore erodes into the next. There's another lesson hidden in this metabolism: fragility. For a comet, outgassing is both life and death. It is how it reveals itself and also how it vanishes. Every vapor trail is a fraction of its mass, lost forever to space. The same sunlight that lets us hear its voice is what erases it. In that way, the comet becomes an image of impermanence, a body defined by the act of disappearing. The more it speaks, the less of it remains. Perhaps that is the quiet paradox of cosmic communication. The universe shares its stories through transformation, not preservation. Stars burn their fuel to shine. Comets evaporate to reveal their secrets. Even we, in the end, radiate away our warmth, our light, our signals into the dark. Knowledge, it seems, always comes at the cost of energy. The universe tells its tale by spending itself. But the loss is never total. What 3I/Atlas released will not vanish. It will become part of something else. The hydroxyl fragments it produced will eventually recombine into water, perhaps within another comet, another planet, or even a molecular cloud far from here. In a few million years, those same atoms could find themselves trapped in ice once again, ready to repeat the cycle. The galaxy's metabolism doesn't end. It simply changes shape. Thinking about it this way changes how we see isolation. The stars that seem distant and separate are, at the atomic level, sharing everything. The vacuum between them is not a void, but a slow-moving river of particles and light. Every comet that falls toward a star, every gust of solar wind, every fragment of dust is part of a single, self-sustaining network. We may look up at the sky and see separation, but the truth is a continuous web of exchange. What travels between stars is not just matter, but memory, the record of what has been and what will be. For humanity, the detection of OH in 3I/Atlas is a reminder that our science is also part of that metabolism. We observe, we absorb, we transform information into understanding. Our telescopes and instruments are extensions of that same universal process, tools that allow the cosmos to study itself. When we point our antennas toward a distant object, it's not just us listening, it's the universe, through us, becoming aware of its own heartbeat. So when you think of 3I/Atlas, try not to imagine a single icy rock wandering through space. Picture instead a tiny droplet moving through the veins of a galaxy, carrying a trace of one star's breath to another. Picture the way its vapor mingled with sunlight, forming a bridge of invisible molecules that briefly connected two stellar systems, and imagine that somewhere, far away, another civilization might one day detect the echo of a comet that came from our own sun, a fragment of our water, our chemistry, our story drifting into their sky. The galaxy's metabolism never stops. It is slow, quiet, and patient. And in every faint line of a spectrum, in every whisper of a molecule, it tells the same truth, that everything is connected not by words, but by motion, by the shared breath of matter moving endlessly between stars. In the high plains of the Karoo, the night feels enormous. The air is thin and dry. The stars look almost close enough to touch. When you stand among the 64 dishes of the Meerkat array, you hear nothing but the sound of the wind sliding through metal. The quiet is deliberate. This remote desert was chosen for its silence, a place so far from radio chatter that even a passing airplane or phone signal would sound deafening. It is, quite literally, one of the best places on Earth to listen to the universe breathe. Each dish in Meerkat is a perfect ear, curved like the inside of a seashell. They work together, connected by a web of underground fibre optics, their data synchronized to the millisecond. When one turns toward a target, all follow, creating an invisible lens the size of a small city. This combination gives Meerkat its power, the ability to distinguish a whisper from billions of kilometers away, buried within the ocean of cosmic noise. That precision was what made it possible to detect the faint absorption lines from 3I/Atlas. When the team began their observation, they were not listening for a message, they were listening for absence, for a small hollow in the flow of radio waves that could only mean something had gently taken energy away. It's a strange kind of listening, almost philosophical. Instead of focusing on sound, you focus on what isn't there. To do that, the array had to be tuned with extreme care. The receivers were set to what astronomers call the L-band, roughly between 1 and 2 billion cycles per second. It's a region of the radio spectrum protected internationally for scientific use, because it includes some of the most important molecular fingerprints in space, especially the hydroxyl frequencies near 1665 and 1667 MHz. Meerkat's location in the Karoo adds another layer of protection. There are no nearby cities, no Wi-Fi networks, no cell towers. Even cars using spark plugs are banned near the array. In this zone of stillness, the universe can finally be heard without interruption. When the data came in that morning, the readings were so subtle that most instruments would have ignored them. But Meerkat's design allows it to combine signals from all 64 dishes into one image, magnifying faint patterns the way overlapping waves build into a crest. Each dish caught the same small dip at exactly the same frequency. Statistically, the chance of that being a coincidence was almost zero. The signal was real. The verification process that followed was methodical. The scientists checked for radio interference from Earth, from satellites, radar, aircraft, or local electronics. Nothing matched. They compared the timing of the dip to the comet's known motion across the sky and found perfect agreement. As the comet moved, the frequency shifted ever so slightly, following the Doppler effect like a moving siren changing pitch. It was unmistakably tied to 3I/Atlas. Then came the confirmation from other instruments. Data from the Swift satellite working in ultraviolet light showed water vapour escaping from the comet at the exact same time. Two completely different ways of listening, one through light, one through radio, told the same story. It's as though two languages had translated the same sentence independently and produced the same meaning. What's remarkable is not just the accuracy, but the calmness of the discovery. There was no thunderous announcement, no cinematic drama. In science, the quietest data often carry the most weight. One of the researchers later said, "It felt like catching a feather in a storm. You know the feather is real because you can feel its touch, but it doesn't fight against your hand. It simply arrives." Meerkat itself is part of a larger dream, a precursor to the Future Square Kilometre Array, or SKA, a global network of radio telescopes stretching across continents designed to act as a single ear for the cosmos. When that system is complete, it will be able to detect radio signals hundreds of times fainter than those we can hear today. But the 3I/Atlas observation shows that even now, we're capable of extraordinary sensitivity. We can detect the breath of water vapour from a world so small it would fit within our own moon's shadow, across distances where light takes hours to reach us. To appreciate the scale of this precision, consider what it means to detect a signal of 1665 megahertz. It's a wave oscillating 1.5 billion times per second, travelling across millions of kilometres. The absorption dip recorded by Meerkat was less than 0.1% deep, like noticing a single drop missing from a waterfall. And yet that missing drop contained an entire story about chemistry, temperature, motion and light. But science doesn't thrive only on sensitivity, it thrives on trust. Before the data was shared, the team spent days rechecking every calibration, making sure no human error had crept in. They recalibrated the system by pointing it toward standard sources, galaxies and pulsars whose radio brightness is known precisely, to confirm the baseline. Every test came back clean. The small hollow at 1665 MHz was no illusion. The comet had absorbed a little piece of the universe's music. This is the beauty of radio astronomy. It lets us hear what eyes cannot see. Optical telescopes show us images, the glowing dust, the tails of comets, the sparkle of stars. Radio telescopes reveal the invisible structure beneath that beauty. They tell us what atoms are doing, how they vibrate, how they interact with energy. They turn silence into language. The process of analysing such data is almost meditative. Long hours pass with screens filled by nothing but lines and numbers, searching for patterns that might mean something. Most of the time, they don't. The universe is noisy. Interference and background, radiation fill every corner of the spectrum. But when a pattern repeats, when it appears exactly where the physics says it should, a quiet certainty emerges. It's the kind of moment scientists live for. Not a burst of excitement, but a slow, expanding calm. The feeling of understanding something that existed long before you and will continue long after. Meerkat's observation of 3I/Atlas was one of those moments. It demonstrated that even without spectacle, even without grand discoveries of alien life or new physics, the simple act of listening can transform our relationship with the cosmos. It showed that interstellar science has matured, that we no longer have to rely on speculation or accidents. We now have instruments precise enough to record the chemistry of visitors from other stars, to watch the metabolism of the galaxy unfold in real time. In the Karoo, the night after the detection, the desert was once again quiet. The dishes stood still, reflecting moonlight. A jackal howled in the distance, one of the few sounds allowed to exist in that vast silence. The sky stretched overhead, filled with the same hydrogen line hum, the same molecular music that has been playing since the universe cooled after the Big Bang. Somewhere up there, the comet was still fading from view, its water molecules dispersing into the solar wind. But the data had been captured, stored, and shared. A small new verse in the ongoing symphony of astronomy. The Meerkat team had shown that patience and precision can uncover voices the universe did not even mean to send. And perhaps that's the quiet triumph of it all. The realization that knowledge doesn't always come from what shouts the loudest, but from what endures long enough to whisper. In the stillness of the desert, among machines built to hear the unhearable, a handful of scientists caught a breath from another star. It was the smallest thing imaginable, and yet in its smallness, it reminded us of something vast. That even across the endless distances of space, the universe still finds ways to be heard. When you think of light, you probably picture brightness, something that dazzles or burns, that reveals colours and outlines. But to an astronomer, light is not always visible. It can move as slow radio waves that stretch wider than mountains, or as sharp X-rays that slice through atoms. What we call light is simply information, a way the universe sends messages across distance. Each wavelength carries a different kind of story, and the story of 3I/Atlas could only be understood when all those voices were heard together. After the radio detection, the Meerkat team wasn't alone in their observation. All over the world, telescopes have been watching the interstellar visitor since it first appeared in July of 2025. Some looked in visible light, tracking the comet's faint tail as it brightened each week. Others used infrared, sensors to measure how warm the surface became as sunlight poured over it. And high above Earth, orbiting quietly in the blackness, the Swift satellite observed the same object in ultraviolet light, the part of the spectrum that our eyes cannot see, but that water molecules respond to most strongly. Each of these instruments saw a slightly different story, like friends describing the same event from different angles. The optical telescope saw a soft glow, a coma of dust spreading around the nucleus. The ultraviolet telescope saw the shimmer of vapour, the moment sunlight broke water apart into hydrogen and hydroxyl, and the radio array, listening from the desert, heard the absorption of those hydroxyl fragments as they drank tiny sips of energy from the background sky. Only by layering these views together could scientists understand what was really happening. A frozen traveller awakening, its ice vaporizing, its chemistry writing itself across multiple kinds of light at once. To visualize that, imagine a glass sphere filled with ice sitting under a lamp. In visible light, you would see it begin to glisten. In infrared, you would sense its warmth. In ultraviolet, you would see the invisible reactions as light splits the molecules apart. Now expand that simple experiment into space, where the lamp is the sun, and the sphere is a comet older than any civilization on Earth. Each wavelength becomes a chapter in its story, each telescope a reader of a different alphabet of light. The pattern observed from 3I/Atlas matched what had been seen in comets before, but with one extraordinary twist. This one came from another star. That fact alone made every detail precious. The ratio of the two hydroxyl lines, the rate of its brightness change, the speed of the tail's motion, all these numbers together confirmed that it behaved like a water-rich comet, not like an artificial object or a dry fragment. It was natural and yet new, a familiar song played by an unfamiliar instrument. The beauty of multi-wavelength astronomy is that it doesn't rely on belief or interpretation. It's confirmation through diversity. If one instrument detects something unusual, another observes from a different perspective to test it. It's like listening to an orchestra from multiple seats in a concert hall. From one side, you might hear mostly the violins. From another, the percussion dominates, but together, the full harmony becomes clear. That is how scientists know that the whisper from 3I/Atlas was not a fluke of equipment. It was a genuine event, confirmed across instruments that measure light in ways our eyes can barely imagine. Among those instruments is the upcoming Rubin Observatory, also known as the LSST, the Large Synoptic Survey Telescope. When it becomes fully operational, it will scan the entire southern sky every few nights, capturing tens of terabytes of data each session. Its goal is to find transients, the fleeting, things that appear and vanish quickly, like comets, asteroids, and supernovae. It will be able to detect interstellar visitors like 3I/Atlas long before they approach the Sun, giving scientists time to prepare coordinated observations across all wavelengths. No longer will we have to wait for luck and geometry, we will have foresight. Then there is the European Southern Observatory's FORMOST project, an instrument designed to collect spectra from thousands of objects at once. Imagine 2,400 eyes spread across the night sky, each splitting light into its component colours to reveal chemical fingerprints. Together with the Rubin telescope, It will make the search for interstellar chemistry systematic rather than accidental. What was once a once-in-a-century event may soon become routine. A new branch of science born from patient collaboration. And high above the Earth, the James Webb Space Telescope continues to explore light in the infrared, capable of mapping the temperature and composition of exoplanet atmospheres. Its instruments can detect the same molecular signatures: water, carbon dioxide, methane, in the glow of distant worlds. While Meerkat hears the quiet hum of hydroxyl, Webb sees the warmth of planetary chemistry. In the years to come, the two will work in tandem, one listening, one seeing, both decoding the same universal language. These observatories are not just machines, they are extensions of human curiosity. Each one represents a different sense: hearing, sight, touch, stretched beyond the limits of biology. Together, they form what some astronomers call the cosmic nervous system, a network of instruments scattered across Earth and orbit, all tuned to the same purpose: to notice change. 3I/Atlas happened to pass through at the right time, a spark of motion triggering a global reflex. For a brief period, the entire planet looked toward one point in space and listened. That kind of coordination will define the future of astronomy. In the coming decade, discoveries will no longer belong to single telescopes, but to networks. When a new object is spotted, data will ripple automatically through observatories around the world. Optical systems will record brightness. Radio arrays will listen for molecules. Infrared telescopes will sense heat. Ultraviolet instruments will track vapor and plasma. Artificial intelligence will knit it all together into a single seamless view, a complete portrait of an event as it unfolds in real time. For the first time, our species will watch cosmic chemistry happen, not in hindsight, but as it breathes. The story of 3I/Atlas may one day be remembered as the first step in that transformation. Before it, each interstellar object was a fleeting curiosity, something we noticed too late, glimpsed and lost. After it, the scientific community began to see the potential of harmony between instruments. The detection of those twin radio lines wasn't just a discovery, it was a rehearsal for the future. Proof that when the universe speaks softly, multiple ears must listen together. There is a quiet beauty in that cooperation. Science, after all, is not unlike the chemistry it studies. Progress happens through interaction. A molecule of water forms when two atoms share electrons. Understanding grows when minds share observations. The same principle that binds hydrogen to oxygen also binds one telescope's data to another's. Connection, whether chemical or human, creates meaning. On the night after the discovery, as the Meerkat dishes turned away from the sun and the last of the data streamed into servers, the desert went still again. But halfway around the world, at another observatory, a different telescope was already scanning the same region of sky. Others followed, in Chile, in Hawaii, in orbit. For a few days, Earth became a single instrument. All its sensors pointed toward one wandering fragment of ice. Each captured a different kind of light. Each added a new verse to the same cosmic song. And perhaps that is the lesson the comet left behind. The universe speaks in many voices: ultraviolet, infrared, radio, visible. No single one is complete. But when we weave them together, when we listen not only with our technology, but with patience and imagination, the whole becomes greater than its parts. In that harmony, we find understanding, not of something distant, but of our own nature as listeners within a universe that is forever singing. When news of the discovery reached the public, the reaction was immediate and, in a way, inevitable. A headline that read, "An interstellar comet just spoke to Earth," sounded almost too poetic to resist. People wondered aloud, was it really speaking? Was the signal artificial? Could it be a message, faint and coded from someone else out there? In the quiet spaces of the internet, the idea began to ripple. Perhaps this was not chemistry at all. but intention. The scientists who made the discovery understood the fascination. Humanity has always carried a kind of homesickness for voices beyond our own. Every telescope, every radio array we've built is a monument to that longing. The desire to not be the only listeners in an otherwise indifferent cosmos. So when something from another star finally spoke, it was natural to wonder whether we had finally been answered. But the truth, as is often the case in astronomy, was both simpler and more profound. The absorption Meerkat detected that morning was steady, unmodulated, and pure. There was no repetition, no rhythm that hinted at language, no structure that could have been designed. It was not a broadcast, but a silence within light, a molecule drinking a sip of energy and leaving a small hollow in the spectrum. If you were to imagine it as sound, it would not be a note played deliberately. It would be the space between notes, the pause that gives music its shape, and that space, that absence, was entirely natural. Still, the notion of absorption as communication caught the imagination of a few thinkers, a poetic speculation more than a scientific one. The idea went like this. If a civilization wished to speak without revealing itself, without sending obvious signals, it could use chemistry itself as a form of expression. It could sculpt the balance of molecules in a cloud, or the ratios of isotopes in a comet, or the timing of vapor release to encode meaning. It would not transmit in radio waves, but in reactions, a message written into the behavior of matter, a chemistry that speaks softly enough to hide within nature. It's an elegant fantasy, one that speaks to our yearning to find intelligence mirrored in the universe's complexity. Yet when examined closely, nature's own processes already look intentional enough. The dance of physics, the way sunlight warms ice, the way atoms vibrate in resonance, the way water fragments into hydroxyl that hums in radio. All of it happens with such harmony that it doesn't need a guiding hand to seem intelligent. In fact, the universe's greatest wonder may be that it creates beauty without trying. For the astronomers at Meerkat, that was the real marvel of the discovery. They were not disappointed that the signal wasn't a message. They were moved by the realization that nature alone could produce something so exquisite, so deliberate in appearance, yet entirely spontaneous. A comet exhaling water, a molecule vibrating, a frequency absorbed, a human ear catching it. 4 simple steps, each bound by physics, and yet together they feel like art. There is an old saying among radio astronomers, nature writes in cursive. It means that the universe's signatures are rarely sharp or mechanical. They flow, they meander, they contain imperfections that make them alive. The hydroxyl absorption lines from 3I/Atlas were exactly like that. Soft at the edges, slightly broadened by motion, graceful rather than rigid. A human-made signal, by contrast, tends to be narrow, precise, and repetitive. Nature, even when it repeats, always improvises, and that improvisation is how we can tell the difference. But the public imagination is a powerful force, and for a few days the idea of a chemical message lingered in the news cycle. People asked what it would mean if the universe had chosen chemistry as its language. Some wrote essays comparing it to the concept of pheromones in biology, signals carried invisibly through air, shaping behavior without sound. Others drew parallels to art, to music without melody, to paintings made of texture and colour rather than form. It was as though the discovery had opened a new metaphor for communication, one that doesn't rely on intention to convey meaning. Even among the scientists there was quiet reflection. One researcher, when asked what it felt like to detect such a signal, said, "It's a reminder that listening is an act of humility. We pointed our instruments not expecting a reply, but the universe spoke anyway, just not in words." That sentiment captures what many in the field feel, but rarely say. Astronomy is not a search for contact as much as it is a discipline of patience, of paying attention to what exists. When you listen carefully enough, even the simplest process, light passing through vapor, becomes a form of dialogue. In a sense, every scientific observation is a conversation between curiosity and reality. We ask a question not with our voices but with our instruments, and the universe answers in its own language, sometimes clearly, sometimes ambiguously, sometimes in riddles we spend lifetimes decoding. The line between natural and intentional often depends on how much we understand. Centuries ago, lightning was thought to be divine anger. Now we know it as electrical discharge. One day, perhaps, we might learn to read chemistry with the same familiarity we now have with light, and what seems like coincidence could begin to look like design. But until that day, the simplest answer remains the truest. Sunlight and ice. Nothing more, and yet more than enough. That simplicity carries its own grace. The same physics that governs comets governs us. The molecules that whispered in radio frequencies are the same ones flowing through our cells. We too are made of atoms that absorb and emit light, that respond to warmth, that remember where they have been. In a way, we are the universe's chemistry, learning to reflect upon itself. When we hear water from another star, we're hearing a version of our own origin story. Not a message written for us, but a message that includes us simply because we exist. It's comforting, then, to think that the universe doesn't need to send deliberate greetings to feel intimate. Its presence is enough. Every star that shines, every comet that exhales, every molecule that hums in darkness, they all carry meaning by existing at all. To insist on intention is to miss the quiet miracle of natural order, the elegance of inevitability. Still, there's beauty in the thought experiment. If a civilization ever did wish to speak quietly, chemistry would be a perfect medium. Reactions are timeless. Molecules survive where technology fails. A shift in the ratio of hydrogen to deuterium, a pattern of isotopes in ice, could carry meaning across millennia. And perhaps somewhere in the deep past or far future, such a message already exists, waiting for someone with the right patience to recognize it. But whether or not that is true hardly matters. The discovery of 3I/Atlas tells us something equally profound, that wonder doesn't depend on intention. Meaning can arise without purpose. A whisper from sunlight touching ice can be enough to change how we see ourselves in the cosmos. The simplest story. Water warming, vapor rising, molecules splitting. It can be as moving as any tale of alien intelligence. So when the excitement faded and the world returned to its ordinary pace, the astronomers felt no disappointment. They had not found a message from beyond, but they had found evidence of something older and deeper. A pattern that connects every world that has ever known warmth. The signal was unmodulated, unencoded and unplanned, yet it spoke to us all the same. Perhaps that is the universe's secret. It doesn't communicate through intent, but through resonance. It hums in frequencies that echo within us because we are made of the same matter. It doesn't whisper to be heard, it whispers because that's what it has always done. And we, for the first time, happen to be listening. The speculation didn't end with the confirmation that the comet's whisper was natural. Instead, it evolved, from wondering if it was artificial to asking how we would know if it ever were. The question was no longer about 3I/Atlas alone. It was about the limits of our listening and the shape that intelligence might take if it chose to speak in ways subtler than words. For more than half a century, the search for extraterrestrial intelligence, or CT, has focused on narrowband signals, artificial tones so precise that nature rarely imitates them. The logic was simple. A single, sharp frequency among the random hum of the universe would stand out like a lighthouse beam across the fog of noise. That method has served us well, but the silence that followed decades of listening has prompted a new thought. What if other minds don't communicate in beams of light, but in patterns of chemistry, in signatures hidden within the ordinary workings of nature? This idea has led scientists to a broader concept, technosignatures. These are not just radio messages, but any observable clue that might suggest technology or deliberate modification of an environment. On planets, that could mean traces of pollutants or unusual gases in an atmosphere, chemicals that nature alone cannot easily produce. Around stars, it could mean odd fluctuations in brightness, as if vast structures were occasionally blocking the light. And within the vastness of space, it could even mean peculiar ratios of isotopes, versions of the same element differing slightly in weight, that hint at artificial refinement. Yet even as the scope expands, the heart of the question remains the same. How can we tell the difference between nature and intention when both are capable of elegance? For 3I/Atlas, the answer was clear. Its signals were entirely natural. But the way that discovery unfolded has reshaped the philosophy of listening. It showed that the border between natural and artificial is porous, though what we call intelligence might not always appear as an engineered object or a message beamed through the stars. It might appear as a pattern, a fingerprint embedded in the very chemistry of light. Imagine a future where telescopes no longer scan the sky for coded messages, but for unlikely harmonies. Instead of looking for a single frequency repeating like a call, they would look for relationships between many frequencies that move together in impossible synchrony. Or they might look for materials that shouldn't exist where they are, rare combinations of atoms that suggest crafting. In that sense, the universe becomes not a silent void to be monitored, but a vast gallery of clues waiting to be noticed. Some researchers have begun to use the phrase post-biological SETI, meaning a search for intelligence that may not think or build the way we do. If life elsewhere has evolved far beyond biology into forms of matter or energy we can't yet imagine, its traces might lie not in messages but in the subtle bending of natural laws. A civilization with technology millions of years ahead of ours could communicate through the shaping of starlight itself, or the arrangement of dust clouds, or even through patterns of molecular absorption, like those we observed in 3I/Atlas. Not because it intends to send messages, but because intelligence, at its core, leaves patterns behind the way wind leaves ripples on sand. This is where the new tools of discovery come in. Astronomers are now training artificial intelligence, machines that can sift through oceans of data, noticing what the human eye might miss. These systems learn by example, studying the symphony of natural processes until they know its rhythm well enough to detect when something is off-key. It's like teaching a musician every piece of classical music ever written, so that if one note appears that doesn't belong, they notice instantly. In astronomy, that stray note could be the first hint of an unnatural event, a pattern of light, or chemistry, or geometry that nature would never choose on its own. The beauty of this approach is that it doesn't presume what form intelligence must take. It listens without expectation. A machine learning algorithm doesn't need to know what it's searching for. It only needs to know what is ordinary so it can highlight the extraordinary. It's the digital equivalent of curiosity, open, patient, and endlessly attentive. And what these systems are beginning to reveal is humbling. They find complexity everywhere. Clouds in the atmospheres of exoplanets shimmer with unexpected mixtures. Pulsar signals display subtle variations that seem almost intentional until physics explains them. Cosmic rays arrive in patterns that border on poetry. Each time we think we've found something too structured to be natural, nature teaches us a new trick. The lesson is not that intelligence is absent, but that the universe itself may be intelligent in its design. One scientist once said, "Maybe intelligence isn't rare. Maybe it's just quiet." That thought changes everything. It suggests that the cosmos doesn't need civilization shouting across space to be alive with awareness. It might already be aware, in the way ecosystems are aware, in the way feedback loops stabilize and adapt. Every star that forms, every comet that melts, every molecule that vibrates in rhythm with sunlight, all of it might be part of a grand unconscious conversation, Intelligence could be a spectrum, not a point, with human language at one end and atomic resonance at the other. This doesn't diminish the search for life. It deepens it. It reminds us that SETI is not only about finding others, but about learning how to listen differently. We once thought of communication as the exchange of deliberate symbols. Now we're beginning to understand it as the sharing of patterns. If an alien civilization ever wished to leave a trace, it might not choose radio at all. It might choose the one medium that never fades, chemistry, a ratio of elements in a distant planet's atmosphere, a repeating molecular imbalance drifting between stars, a kind of quiet beacon written into matter itself. And perhaps that's what the discovery of 3i/Atlas ultimately gave us. Not a message from beyond, but a new form of hearing. It taught us to look for intelligence not in what breaks the rules of nature, but in what uses them beautifully. To recognize that the same laws that shape molecules could, in the hands of awareness, become tools for meaning. It's tempting to think that we would know immediately if we were contacted, that a message from another world would stand out unmistakably. But maybe it already has, not as a signal, but as an idea, a shift in perception. The universe has been broadcasting for billions of years in the form of stars, atoms, and the chemistry of light. Only now are we learning to tune ourselves to its frequency. And so, the search continues, not in desperation, but in reverence. Each new telescope, each algorithm, each dataset is a small extension of our senses into the unknown. We're not shouting into the void, we are whispering and waiting for echoes. Whether those echoes come from other minds or from the universe itself no longer matters as much. What matters is that, for the first time, we are learning to truly listen. Perhaps that is the real meaning of the 3i/Atlas signal. It wasn't a transmission but an invitation, a reminder that the cosmos is not silent, and that meaning doesn't always come with intention. Sometimes, the universe speaks simply by existing, and when we notice, we become part of the conversation. Maybe that's the quiet miracle of this moment in history, that through chemistry and curiosity, the universe has taught us how to hear its heartbeat, and just maybe, how to hear our own. In the weeks following the detection, astronomers kept their telescopes trained on 3i/Atlas, watching it drift around the sun and begin its long journey back into the cold. What they saw next was both strange and familiar, the kind of beauty that only reveals itself when sunlight meets ice at the edge of endurance. The comet's tail began to sway. At times it split into two, like mirrored ribbons of dust fluttering in a cosmic breeze. Other nights, it twisted and wobbled as if the body beneath it were turning in sleep. Comets are not solid sculptures. They are fragile, breathing things. They are made of rock, dust, and frozen gases that have spent millions of years locked in silence. When warmth reaches them, they awaken in unpredictable ways. One patch of ice begins to sublimate, to leap directly from solid to vapour, while another remains frozen. Jets of vapour erupt unevenly, nudging the comet ever so slightly off its course. To an observer, these tiny releases appear as flickers of light, bursts of movement, subtle changes in direction. Astronomers call this outgassing, but the word feels too mechanical for what it truly is. It's more like the exhalation of a being that's been holding its breath since the dawn of another star. Each pulse of vapour carries away grains of dust, forming the glowing tail we see from Earth. As the sunlight shifts, the jets switch on and off, creating an impression of motion, a flag trembling in the solar wind. In the case of 3i/Atlas, the wobble was unusually regular. Its light curve, the pattern of how its brightness changed over time, rose and fell smoothly, about half a magnitude every week. That meant the entire body was rotating, exposing different surfaces to the sun in a gentle rhythm. It wasn't tumbling chaotically like some comets do. It was spinning like a slow dancer, turning to face the light and then turning away. The comet's shape likely played a role. Many comets are not spherical but elongated, more like potatoes or loaves of bread than perfect spheres. As they rotate, the uneven distribution of mass creates variations in sunlight exposure, which in turn causes asymmetric jets of vapour. The result is a kind of feedback loop. Sunlight heats one side, jets push from that side, rotation changes, new areas warm, and the process repeats. To describe it in plain terms, the comet breathes, and with every breath it moves a little differently. What makes this dance even more delicate is the scale. The jets themselves are almost invisible, releasing perhaps a few hundred kilograms of water vapour every second, roughly the weight of a small car. That might sound enormous, but in cosmic terms it's nothing. The comet's total mass would be trillions of times larger. The resulting thrust is weaker than a feather brushing against your hand, and yet, over time, it changes everything. Tiny pushes accumulate, altering the trajectory enough that astronomers can measure it from millions of kilometers away. That small deviation is what's known as a non-gravitational acceleration, movement not caused by gravity, but by the comet's own activity. It's the same phenomenon that caused confusion with Oumuamua, the first interstellar object discovered in 2017, whose unexplained acceleration sparked debates about alien technology. But in 3I/Atlas, the explanation is far less mysterious. The presence of water vapour confirmed by the hydroxyl lines means outgassing is both real and measurable. The comet isn't steering itself, it's being guided gently by its own breath. Still, the image is haunting. A body from another star system crossing the inner solar system like a visitor, propelled only by its own melting skin. Each exhale changes its course slightly, turning its journey into a story written in vapour. There's poetry in that physics, a reminder that motion itself can be fragile, that even in the great clockwork of orbits, softness has power. The tail, too, carries layers of complexity. To the naked eye, a comet's tail looks like a single luminous stream stretching away from the sun. But in reality, there are two. One is made of dust, tiny grains pushed by the pressure of sunlight. The other is made of ionized gas, charged particles swept along by the solar wind. The two tails often diverge at slight angles, creating an ethereal fork in the sky. When viewed from certain perspectives, one tail can appear reversed, pointing toward the sun rather than away. This anti-tail is an optical illusion, a trick of geometry, but to human eyes it feels almost mystical, as if the comet were balanced perfectly between attraction and release. Photographs taken during 3I/Atlas's closest approach show exactly that. A twin-tail formation, symmetrical and pale, glowing faintly blue where ionized water molecules reflected sunlight. Astronomers noted that the pattern persisted for days, wobbling slightly as the rotation of the nucleus shifted the direction of its jets. It was not a beacon, not a signal, but it looked uncannily like one. A geometry so precise it seemed to flirt with meaning. To some observers, it brought to mind the fragile balance of systems everywhere, how even a frozen object, buffeted by solar wind and radiation, could maintain rhythm and grace. The symmetry was not designed, but it gave the impression of design, the kind of coincidence that feels intentional simply because it is beautiful. When researchers modelled the behaviour, they found that the tail's pattern could be explained entirely by natural mechanics. The comet's rotation period, likely between 10 and 12 hours, caused jets to flare in repeating arcs. The combined effect was a gentle oscillation that made the tail appear to breathe, and as the comet moved farther from the sun, the pattern slowed, dimmed, and finally disappeared, the breath subsiding into silence once more. There's a kind of empathy that creeps in when studying such phenomena. We begin to describe comets as living things, not because we believe they are, but because their behaviour mirrors our own cycles of wakefulness and rest. They lie dormant for ages, then come alive under warmth, shed a part of themselves, and return to sleep. The process is mechanical, yet it feels emotional. Even rocks, it turns out, have moods, not in the sense of thought, but in the sense of rhythm, of response. The universe may not feel, but it reacts, and that reaction can look remarkably like feeling. The subtle trajectory shifts observed in 3I/Atlas were small, mere fractions of a degree, but they reminded scientists that everything in the cosmos is in negotiation. Gravity pulls, light pushes, and objects find compromise in motion. Nothing travels a perfect path. Every orbit is slightly rewritten by the forces that touch it. In that sense, the comet is a lesson in humility. It shows that persistence doesn't mean rigidity. To endure, even ice must yield. By the time 3I/Atlas reached its outbound leg, moving away from the sun, its activity had diminished. The jets quieted, the tails faded. The bright exhalation that had once been visible even through small telescopes dwindled into darkness. But the data, the wobbles, the shifts, the gentle accelerations, stayed behind, written in numbers and plots that future scientists will study for years. Each point in that data tells a story of how fragile motion can be, and how beauty often emerges not from control, but from surrender. If the comet had a voice, perhaps it would say nothing more than this: that to move through the universe is to change, and that change, no matter how small, is the price of warmth. It would speak not in words but in balance, between sunlight and shadow, between gravity and breath. And for a moment, while its tail trembled and its ice turned to vapour, it showed us that even in the coldest corners of space, there is room for grace. By the time 3I/Atlas began to fade from view, astronomers knew they were witnessing a kind of slow and beautiful dying. Every comet lives by the same paradox. Warmth gives it life, but also takes it away. The sunlight that wakes its frozen heart is the same force that erases it, molecule by molecule. Watching such a process unfold is like listening to a candle melt, delicate, steady, and inevitable. At around -40 degrees Celsius, or about 230 degrees above absolute zero, water ice begins to breathe. Below that threshold, the molecules remain locked in their crystalline lattice, stiff and unmoving. But as the comet nears the sun, even the faintest warmth causes vibration. The molecules start to slip free, one by one, escaping into the vacuum. There is no liquid phase in this emptiness, no dripping, no flowing, just a direct transformation from solid to vapour. It is evaporation without melting, an exhalation into silence. The comet's other ingredients, carbon dioxide, carbon monoxide, ammonia, methane, all have lower boiling points. They would have vanished long ago, either during earlier orbits in its home system or on the interstellar journey itself. What remains is the most stubborn and familiar of volatiles, water. And that persistence is why 3I/Atlas glows with the particular frequency we heard in the Meerkat data. Hydroxyl, the fragment that sings at 1665 and 1667 MHz, is water's echo, the ghost of what sunlight destroyed. It's easy to imagine this process as violent, but in truth it's gentle, more like sighing than screaming. Each second, billions upon billions of molecules leave the surface, expanding outward at about 1 kilometre per second. That sounds swift, but space makes everything feel slow. The vapour spreads into a vast invisible sphere around the comet, and within that sphere ultraviolet light breaks the water into fragments. The average lifespan of a hydroxyl molecule under such light is around 100,000 seconds, about a day. Then it too breaks apart or drifts away. So every day the comet exhales and every day its breath dies. Nothing remains static. Even chemistry has a pulse. The molecules that survive move outward into the solar wind, mingling with particles from the sun, scattering into trails that eventually fade into the dark. In the end, all that remains of the comet's outburst is a faint stream of dust and memory. This cycle, breathing, fading, repeating, defines the last stage of every comet's life. Each orbit, each approach, each brush with warmth carves it smaller. Eventually it becomes a fragment, then dust, then nothing. In the case of an interstellar traveller like 3I/Atlas, there may never be another orbit. Once it leaves the solar system, it will drift forever into the galactic night, its surface hardened, its vapour gone, its ice reduced to a whisper of frost. What began as a bright reactive body will end as a dark stone. Yet even in that silence, it continues to move, a fossil of a moment when chemistry met light. For scientists, these fading phases tell a story about endurance. The fact that 3I/Atlas still contains so much water after millions of years between the stars means its ice was remarkably stable. That stability challenges our understanding of how volatile materials behave in deep space. Interstellar radiation is harsh, full of cosmic rays and ultraviolet photons that can slowly erode surfaces. For the comet to survive intact, it must have been shielded, perhaps by a crust of dark organic compounds, the kind formed when sunlight cooks carbon-rich ices over time. In a way, its skin was its memory, scarred, protective and wise. When light finally broke through that outer layer, the buried water reawakened. The radio lines we detected weren't just signs of evaporation. They were the sound of age giving way to renewal. The comet was losing part of itself, but in doing so, it revealed what it had preserved. The same pattern holds everywhere. In stars shedding gas to form new stars, in planets losing atmospheres to make room for change, even in living beings trading energy for awareness, to exist is to transform, and to transform is to release. Astronomers studying the chemical evolution of comets often refer to a concept called volatile depletion, the gradual loss of easy-to-evaporate materials during interstellar travel. It's an ungainly phrase for something heartbreakingly poetic, the slow simplification of matter by time. As molecules escape, what remains becomes purer, simpler, distilled by endurance. 3I/Atlas, with its water-rich composition, is a survivor of that purification. Its carbon monoxide and nitrogen ices have long since vanished, its lighter gases dispersed, leaving behind only water and dust, the last, most stubborn record of its origin. You could say that by the time we heard it, the comet had already spoken most of its story in silence. The final lines were written in vapour, brief and beautiful, then erased by sunlight. Every atom that left its surface began a new journey, some into the solar wind, some perhaps toward the magnetic field of Jupiter, some into the wider galaxy. None will return to the same body, but all will find new homes. A hydrogen atom might join a cloud that one day becomes another star. An oxygen atom might settle into a dust grain that seeds another planet. The comet dissolves, but its essence circulates. Nothing is truly lost. It only changes audience. Even time itself feels different when you think this way. The 100,000 seconds of a molecule's life seem short compared to the million years of the comet's journey. Yet, from the molecule's perspective, if it had one, those moments are everything. It experiences the warmth of light, the thrill of release, the drift into vastness, and then the fading. That arc, from stillness to motion to silence, mirrors the story of the comet and of us. It's the same pattern, scaled infinitely. Some astronomers describe the tail's fade-in as a quiet death. But in truth, it wasn't death at all. It was a redistribution, a letting go. Each release of vapour, each fragment of ice that turned to gas, carried the comet's story outward. And in that outward motion lies continuity. When sunlight touches what remains, even the faintest dust can still reflect light, still shimmer, still tell the tale of what once was. There's a kind of peace in that thought. that impermanence is not loss, but participation. Every atom leaving the comet's surface will someday belong to something else. The universe does not throw anything away. It recycles, reuses, reincarnates. It turns endings into beginnings so seamlessly that the boundary between them disappears. What we call disappearance is only transition. What we call silence is only another form of sound too faint for us to hear. As 3I/Atlas faded into the depths beyond Mars, the instruments that once listened to it turned towards new targets. The data was archived, the signals catalogued, the stories summarized, but in the minds of those who watched it, something lingered, a quiet awe at the fragility of matter and the generosity of motion. They had seen a visitor burn its own body to speak, and in that burning, they had glimpsed the continuity of all things. Perhaps in the cold dark ahead, the comet will someday pass near another star. It will warm once more, briefly, shedding the last of its frozen breath into a new sky. Somewhere, another civilization, or simply another patient listener, might catch the same faint frequencies, the same twin signatures of water meeting light. And when they do, they might feel what we felt, not wonder at the exotic, but recognition of the familiar. Because in the end, all comets, all planets, all beings share the same quiet truth. To live is to radiate, to be touched by warmth, and to give something back. The light that awakens us also transforms us. And even as we fade, the universe keeps what we were, carrying it forward into endless dawns. There is a point, somewhere between physics and poetry, where chemistry begins to resemble thinking. Not in the way we recognize as thought, not in language, or logic, or memory, but in the quiet rhythm of reaction and response. If you step far enough back, the line between a molecule rearranging itself and a neuron firing in the brain begins to blur. Both are patterns, both are exchanges of energy, both are ways that matter learns to recognize and react to itself. When scientists listened to 3I/Atlas, they weren't just hearing water. They were hearing a process, a conversation between sunlight and ice, energy and structure. In that conversation lies the same principle that, on Earth, eventually gave rise to life. Chemistry learns. It doesn't need intention to evolve complexity. It only needs time and repetition, the same two ingredients that create understanding in any form. Perhaps intelligence, what we call mind, is simply what happens when chemistry learns to dream. When patterns of reaction become so intricate that they start reflecting on themselves, remembering, predicting, imagining. The difference between vapor dancing in sunlight and neurons firing in the human brain is not a difference of kind, but of scale and depth. Both are forms of resonance, energy echoing through matter, trying to maintain coherence for a little longer before entropy dissolves it again. When the hydroxyl molecules in the comet absorbed radiolight at 1665 MHz, they were, in a way, demonstrating the first step toward awareness, sensitivity, the ability to interact with an environment, to respond to change, to leave an imprint. From that foundation, nature has built everything, from cells that sense temperature to minds that sense meaning. The vibration of a molecule is not consciousness, but it is its ancestor. It is the first heartbeat of awareness, long before thought existed to name it. If you could slow time enough to watch the story unfold, you would see chemistry building itself upward. Dust grains stick together to form ice. Light interacts with that ice to form new compounds. Molecules combine into organics. Organics cluster into membranes. Membranes begin to copy themselves. Copying leads to variation. Variation to selection. Selection to survival. And after billions of such cycles, a network of neurons wakes up on a small blue planet and looks back toward the sky, hearing the same frequencies that once whispered in its chemical past. The symmetry of that is difficult to ignore. The same physical laws that shaped hydroxyl in 3I/Atlas also shape the water in your body. The same sun whose light broke the comet's ice is the one that fuels your heartbeat. The same quantum transitions that let those molecules absorb radio waves are the ones that let your eyes see colour, your ears hear sound, your mind form thought. When you trace it back far enough, there is no dividing line between the comet's chemistry and ours. There is only continuity, the gradual organisation of matter into patterns that endure. It makes sense, then, to think of intelligence not as an anomaly, but as an inevitable expression of physics. Once the universe learned to form atoms that could bond, thought became a possible future. And perhaps that's what makes the discovery of interstellar water so profound. It's not that we found something alien, it's that we found something familiar, a reminder that the seeds of complexity exist everywhere. Every droplet of water, every hydroxyl molecule humming in sunlight, carries within it the potential for awareness. Given enough time and stability, chemistry learns structure. Given structure, it learns to sense. Given sensing, it learns to remember. And memory, in its simplest form, is the beginning of thought. If the comet's vapour could think, what would it remember? Maybe nothing in words, but something in feeling. The warmth of its parent star long ago, the silence between stars, the brief touch of another sun's light. Those are experiences without minds, yet they follow the same pattern as our own: stimulus, reaction, echo. In that sense, the universe itself is a great mind, exploring its own possibilities through cycles of cause and effect. Each atom is a neuron, each reaction is a synapse, and we, as conscious beings, are simply one of the universe's latest attempts at self-reflection. You could think of this as a kind of cosmic learning process. Over billions of years, matter has been testing configurations, from molecules to ecosystems to civilizations. Each one a new way for the cosmos to understand itself. Not in words, not in sentences, but in structure. A spiral galaxy is an idea expressed in gravity. A comet tail is a sentence written in sunlight. A living brain is a metaphor built from hydrogen, carbon, nitrogen, and oxygen, the same ingredients that drifted between stars. Seen that way, 3I/Atlas becomes something more than an object. It becomes a bridge between worlds, not just spatially, but conceptually. It connects the chemistry of deep space to the consciousness of the beings observing it. When astronomers turned their antennas toward that faint dot near the sun, they weren't just measuring molecules. They were listening to an earlier form of themselves. They were hearing the first note in a song that eventually became mind. There is a quiet comfort in this continuity. It suggests that intelligence is not something the universe occasionally produces, but something it gradually becomes. Every process that increases complexity, from the formation of a snowflake to the structure of a thought, is part of that unfolding. The cosmos in this sense is not inert, it is learning, slowly, patiently, across scales of time that make our lifetimes seem like moments. This perspective changes the way we see both life and death. When a comet evaporates, it is not ending but contributing, adding its material, its patterns, its lessons to the collective library of the cosmos. When a star burns out, it seeds new stars. When a mind fades, it returns its energy to the same cycle. Every dissolution feeds new organisation elsewhere. What we call decay is simply reorganisation at a higher level of understanding. Perhaps that's why we find such beauty in observing the simplest physical processes. When we watch a comet sublimate or a molecule vibrate, we're watching the fundamental act of becoming. We're seeing the universe do what it has always done: respond, adapt, continue. There's a deep tenderness in that, a reminder that we too are part of the same process. Our thoughts are not separate from physics. They are physics, shaped into introspection. If intelligence is chemistry learning to dream, then 3i/Atlas is a page from an earlier dream, one written in ice rather than neurons, in radio absorption rather than language. We listened to it, and for a moment the distance between molecule and mind disappeared. We recognized ourselves in the pattern, in the rhythm, in the quiet inevitability of reaction. And maybe that's what the universe has been waiting for all along, not to speak to us, but to be recognized by us. Every act of listening brings it closer to awareness. Every discovery is the cosmos realizing something new about itself through us. In that way, the story of 3i/Atlas is not about an interstellar comet passing through our sky. It's about the awakening of understanding. The realization that thought and matter, mind and molecule, are threads of the same vast tapestry. When chemistry becomes thought, the universe no longer feels distant. It feels intimate, almost tender. Every frequency, every vibration, every faint signal becomes part of a single conversation, the cosmos quietly thinking out loud, and we for once listening closely enough to hear it. If you imagine the universe not as a machine but as a mind, then every observation becomes a moment of awareness. Each flash of light, each vibration of a molecule, each thought in a human brain is the cosmos recognizing itself, however briefly. It doesn't think in sentences or equations, but in interactions, the quiet exchange of energy between things. When astronomers detected the faint absorption lines of hydroxyl from 3i/Atlas, they were not just recording chemistry, they were participating in that process of recognition, turning the universe's attention back upon itself. The more we learn about nature, the more it resembles a self-correcting memory. The same laws that create stars also destroy them, recycling their ashes into new forms. The same processes that shatter molecules also forge more complex ones. Everywhere we look, feedback loops govern motion and structure. When sunlight touches ice, it doesn't simply warm it. It triggers a cascade of reactions that feed into the next cycle of creation. When a comet releases vapor, it leaves trails of material that may one day seed another world. What looks like chaos is, on closer inspection, recursion. The universe refining itself through repetition. Perhaps that's what makes consciousness possible at all. If you zoom in far enough, awareness is simply the ability to integrate feedback, to notice change and adjust to it. A molecule notices light and absorbs it. A cell notices its environment and adapts. A brain notices its own thoughts and begins to wonder. Each is a new layer of responsiveness built atop the last. The difference between a comet exhaling water and a mind reflecting on its own existence is one of complexity, not of essence. Both are forms of interaction. Both are the universe learning about itself in real time. There's an elegance to this progression, as if matter were rehearsing consciousness long before life appeared. The same feedback that governs atoms eventually builds organisms, ecosystems, civilizations. And with each step, the patterns grow more intricate, the reflections more detailed. Humanity's telescopes and satellites, the very instruments we use to explore, are extensions of that process. They are the neurons of a larger awareness, tools that allow the cosmos to perceive its own workings at scales no single mind could grasp. When we point our antennas at a comet from another star and decode the shape of its vapor, we're not separate observers looking in. We're the universe looking out, testing what it can know of itself. The act of observation becomes part of the story, like a mirror reflecting not just an image but the act of reflection itself. The more we study the world, the more our understanding alters it, not physically, but perceptually. Knowledge changes the knower. The universe, through us, gains new forms of self-description. If atoms are the letters, then chemistry is the grammar. Planets are the sentences, stars are the paragraphs, and life is the growing vocabulary. Consciousness, then, is the poem the universe writes about itself. An ongoing composition in which every discovery is a verse and every act of curiosity a rhyme. The story doesn't need an author. It writes itself simply because it can. Existence is its own form of literature. There's a gentle humility in viewing the cosmos this way. It frees us from the illusion of separation. The comet we observed, the instrument we built to hear it, and the minds that interpreted the data are all parts of a single continuous mechanism of learning. Each depends on the others. The molecules of 3I/Atlas interacted with sunlight. Those interactions created a pattern. Our detectors recorded it. Our neurons processed it into meaning. What began as a vibration in space ended as understanding in a mind. The circuit closed. The system learned. This concept, that the universe learns, may sound abstract, but it's grounded in science. In physics, every process involves the transfer of information. Even the simplest particle collision carries data about energy and direction. Thermodynamics teaches that information cannot be destroyed, only transformed. Entropy, often described as disorder, is really just the spreading of information across larger scales. The universe is constantly computing, rearranging, and storing data in every interaction. It doesn't think like we do, but it remembers. Seen in this light, life and consciousness are not accidents, but continuations of a cosmic trend toward complexity. The same rules that make a molecule absorb a photon also allow a brain to absorb an idea. The difference is one of hierarchy, a fractal pattern repeating upward. The hydroxyl lines from the comet, the neurons firing as we interpret them, the language we use to describe them, all are manifestations of a single process, the transformation of energy into meaning. This doesn't make the universe mystical, it makes it participatory. We're not outsiders studying a distant system. We are the system, temporarily aware of its own operations. When the Meerkat Array captured that faint signal from 3I/Atlas, it was not just Earth learning about an interstellar comet. It was the cosmos, through the lens of human instruments, hearing one of its own atoms speak back after a journey across the dark. Awareness is circular. The act of listening completes the circuit of being. You could say that curiosity itself is the most natural phenomenon in existence. It's the impulse behind everything that evolves, the tendency of energy to explore new configurations. Stars explore fusion. Molecules explore bonding. Minds explore meaning. Curiosity is how the universe expands inward, even as it expands outward. It is the same force that drives a comet to release vapor and a scientist to ask why. In both, there is movement toward expression. As we build more powerful instruments, the Rubin Observatory, the James Webb Telescope, the next generation of radio arrays, we're increasing the resolution of that self-reflection. Every new tool is a new sense. Each allows the universe to look a little more closely at itself. The data flows through fiber optic cables like neurons through synapses, connecting observatories, computers, and minds into a planetary network of perception. Humanity, without fully realizing it, is constructing a nervous system for the cosmos, one capable of awareness on scales far beyond our individual lives. This perspective also changes how we think about meaning. It suggests that purpose isn't something imposed on the universe from the outside, it's something that emerges naturally from connection. Every system that links energy and information develops tendencies, preferences, feedback. Those tendencies are what we experience as purpose. A sunflower turning toward the sun, a comet turning vapor into light, a civilization turning curiosity into understanding. None of these are random. They're continuations of the same principle, the drive toward coherence, and coherence in turn is the root of beauty. The symmetry of a snowflake, the orbit of planets, the rhythm of a poem, all are examples of energy finding balance through repetition and variation. The universe doesn't create beauty deliberately, but it creates conditions where beauty becomes inevitable. When we call something beautiful, what we're really recognizing is harmony, the resonance between one form of order and another. In that sense, beauty is the universe's way of confirming that it has learned something true. When 3i/Atlas sang its soft song of water meeting sunlight, it wasn't performing for us. It was simply being what it was. A piece of the universe continuing its long education in transformation. But by noticing it, we completed the lesson. We turned reaction into realization, process into poetry. The cosmos learned a little more about itself, not through gods or prophecies, but through patience and attention. And perhaps that is the quiet revelation beneath all of science. That to study the world is to participate in its self-awareness. Each measurement is a mirror, each discovery a moment of reflection. The comet's vapour may have been fleeting, but the understanding it sparked will endure. Part of a growing memory that the universe keeps through us. If chemistry is the first word of creation, then consciousness is its first sentence. And the universe, through countless forms and voices, continues to write, not toward an ending, but toward understanding. Every molecule, every star, every human thought is a syllable in that unfolding poem. And for a brief time, through instruments made of metal and minds made of water, we have been given the privilege to read a few lines aloud, softly, into the dark. Long after 3i/Atlas faded into the deep, astronomers began preparing for what would come next. Because if there was one lesson hidden in that fleeting signal of hydroxyl and sunlight, it was that interstellar visitors are not miracles, they are inevitabilities. The galaxy is full of fragments cast out from planetary systems, ice, dust, rock, the discarded remains of star formation. They drift for millions of years, following paths that eventually intersect other suns. And now, for the first time in human history, we have the instruments and awareness to notice them. The next generation of observatories, led by the Rubin Observatory's legacy survey of space and time, will turn this inevitability into a routine. Starting soon, it will photograph the entire southern sky every few nights, capturing billions of stars and countless moving objects. In its sea of data, software will sift for anything unusual. Points of light moving too fast, following orbits that defy solar origin. Each one could be another interstellar traveller, another piece of chemistry carrying a story from beyond. Scientists expect that in just a few years, we may detect dozens of such visitors every orbit of Earth around the Sun. It's a strange thought, that what once felt like a once-in-a-lifetime event could become something ordinary. Yet in that ordinariness lies transformation. For the first time, humanity will not have to wait for chance alignments like the one that made 3i/Atlas visible near the Sun. We will have warning, time to prepare, time to listen. When a new object appears, the Rubin telescope will send an automatic alert within seconds. Other observatories, in radio, optical, ultraviolet, and infrared, will immediately adjust their gaze. A global network will awaken, like an orchestra tuning itself in perfect unison. Imagine it. A faint moving dot appears in the Rubin data. Within minutes, radio telescopes in South Africa, China, and the United States begin listening for molecular signals. The swift satellite turns its ultraviolet eyes toward it, searching for the glow of vapour. The James Webb Telescope, high above Earth's shadow, measures the warmth of its dust. Across continents, data flows together, billions of bits of light and frequency, merging into a single narrative. The first few lines may tell of water, or carbon, or something unexpected. And once again, we will learn a new dialect in the language of chemistry. This orchestration, human and machine, Earth and orbit, is one of the quiet triumphs of modern science. It's not about grand discoveries or single moments of revelation. It's about the slow evolution of coordination, the way technology mirrors nature's own networks. The telescopes are like cells in a larger organism, each contributing to the same metabolism of understanding. When the next interstellar visitor arrives, it won't be greeted by a single observer, but by a planet listening together. What we'll discover from this new era may change how we think about our own origins. Every visitor carries a fingerprint of its home, the isotopes of its elements, the mixture of its ices, the patterns of its dust. By studying enough of them, we will begin to map the diversity of planetary systems across the galaxy without ever leaving our own. Each comet is a letter from a distant sun, and together they may spell out the story of how matter evolves across the Milky Way. Some may be rich in carbon, others in nitrogen, some with traces of metals that hint at nearby supernovae. A few might carry compounds we've never seen, molecules that could rewrite our understanding of prebiotic chemistry. Each one will remind us that our solar system is not unique, but part of a much wider spectrum of possibility. To most people, the arrival of such an object will look like nothing: a small dot on a telescope screen, a name in a database. But to the scientists who listen closely, it will feel like a heartbeat. They will hear, once again, the sigh of water vapour, the hum of molecular bonds under sunlight, the cosmic whisper of warmth touching ice. And in that sound, that gentle pattern of absorption, will be the reassurance that the universe still moves in harmony with itself. It's easy to romanticize these visitors as messengers, as if they come with intent. But perhaps their beauty lies precisely in their indifference. They are not sent, they simply arrive. They are not trying to communicate, yet they do, through chemistry, through light, through motion. The message is always the same: connection. The same molecules that form in the darkness of another star's nursery behave the same way here. They vibrate at the same frequencies, dissolve in the same light, and hum with the same energy. The physics that binds them is universal, and so, in a way, is the meaning. Every new detection, every interstellar object will deepen that truth. We're beginning to measure how common water is beyond our sun. We're learning how often organic materials survive the long voyage between stars. We're starting to see that the building blocks of life, the simple unions of hydrogen, oxygen, carbon and nitrogen, are not rare, but fundamental. Life, in its potential, is not a cosmic exception, but a cosmic habit. And yet, for all its vastness, this discovery remains profoundly human. It speaks to the instinct that drives us to look up at night, to wonder what else breathes in the dark. We've spent centuries building tools to extend our senses, and what we find is both humbling and comforting. That the universe is not empty but fertile, not silent but humming, not indifferent but deeply coherent. Each comet we study, each molecule we detect, reaffirms that we belong here, not as intruders in a cold expanse, but as participants in its unfolding rhythm. There is something deeply emotional in knowing that we are now capable of this kind of listening. For most of history, we imagined ourselves separate from the cosmos, fragile beings adrift beneath indifferent stars. Now we know the truth is gentler. The same particles that once drifted between the stars now compose our oceans, our clouds, our breath. When we study a comet like 3I/Atlas, we're not just looking outward, we're looking backward, toward the chemistry that became us. When the next visitor arrives, and it will, we will meet it differently, not as strangers, but as relatives long separated by distance. We will read its spectra like a family letter written in the shared handwriting of physics. Its message will not be one of revelation, but of continuity. I am made of the same things as you. I travelled far, but the rules are the same. The story continues. And maybe, in the quiet of that realization, we'll feel what the universe has been telling us all along. That meaning doesn't have to be imposed. It simply emerges wherever matter interacts with light, wherever curiosity meets patience, wherever observation becomes understanding. Each comet is a message not written for us, but perfectly legible when we're ready to listen. The next one will come, and then another, and another still. One day, the discovery of water from another star will no longer make headlines. It will be as ordinary as rain. And yet, even then, the wonder will remain, not because the message is new, but because we will finally have learned how to hear it fully. So when the Rubin Observatory begins its watch, and the sky fills with moving points, remember this: every one of them is a traveller, carrying within it the memory of another world. Each one is proof that the galaxy is a living system of exchange, that nothing, not even ice, stays home forever. And as long as we keep listening patiently and gently, the universe will keep replying, not with words, but with light that behaves just as it always has, softly telling us, you are part of me, and I am part of you. By late November of 2025, 3I/Atlas had already slipped beyond the orbit of Mars, shrinking in brightness each night until even the largest telescopes could barely trace its fading tail. Its brief encounter with our sun, a few weeks of warmth after millions of years of cold, was over. What remained was a trail of dust so thin it would never be seen again, and two frequencies preserved in data files, 1665 and 1667 MHz. Two quiet notes, two coordinates in the spectrum of existence, marking the moment when an alien molecule spoke and Earth listened. When the last observations came in from Meerkat, the scientists knew that the comet's voice was fading. The absorption lines grew shallower day by day, the signature of hydroxyl molecules vanishing as sunlight weakened. There was no sadness in the data, just a kind of serenity, the natural closing of a cycle. The comet had come, breathed and moved on. In its silence there was completion. To picture it now is to imagine a dim ember drifting through the solar wind. Its surface, once glistening with frost, has darkened into carbon black crust. The jets that once whispered water into space have quieted. The tail, which once shimmered like a silk ribbon, has dissolved into an invisible haze. And yet, something of that moment, that tiny interaction between sunlight and ice, still exists, carried outward as waves of energy, as ripples in the electromagnetic sea. Those ripples will keep travelling, crossing the orbits of outer planets, passing the boundary of the heliosphere, moving through interstellar space. They will spread thinner and fainter until they blend with the background hiss of the cosmos, the soft afterglow of the Big Bang itself. But technically they will never vanish. Every vibration, every photon, every particle of energy that touched 3I/Atlas will continue its journey for eternity, carrying within it the memory of that brief breath. It's comforting in a way to think that even the smallest moment in the universe leaves a trace that cannot be erased. When light meets matter, it changes both. When water meets sunlight, it releases a voice that carries outward forever. The comet's final sigh, that gentle pair of frequencies, will outlast every human life, every civilization, perhaps even our planet itself. Somewhere, far away, in a future we cannot imagine, those same frequencies will still be moving through space, like echoes from a dream that refuses to end. For the scientists who spent weeks watching that dream unfold, the aftermath was strangely quiet. The excitement of discovery gave way to reflection, to long evenings spent reviewing data, refining measurements, writing the story of what they had seen. But science has its own kind of poetry. Even when the instruments fall silent, the meaning continues to resonate. Each dataset becomes a fossil of curiosity, a record of a moment when the universe revealed itself in just the right way. And in that silence, new questions began to form. If 3I/Atlas carried water, how many others do? How far does chemistry travel across the galaxy? Could the ingredients of life, the carbon compounds, the amino acids, the frozen whispers of prebiotic matter, be wandering everywhere, waiting to fall into the right orbit, the right warmth, the right chance. If the comet's vapor was a sentence written in the universal language of molecules, how many other sentences are still drifting out there, waiting for us to learn how to read them? There was a moment, one researcher recalled later, when she realized that the data they had gathered was not only about a comet, but about perspective. We didn't just detect water from another star, she said. We detected ourselves, in another form, from another time. Her words captured something profound. The more we look outward, the more we see reflections of what we already are. Our oceans are the same chemistry that the comet exhaled. Our bodies carry the same hydrogen, the same oxygen, the same cosmic dust. The difference is only that for a little while we're warm enough to think about it. That warmth, fleeting, fragile and full of questions, may be the universe's rarest phenomenon. It's easy to see 3i/Atlas as a traveller, but perhaps we are travellers too, orbiting our own brief moment of awareness before fading into whatever comes next. The comet's passage reminds us that all journeys, no matter how long, are temporary. Everything that moves through space eventually becomes dust again, and yet, in that transience lies beauty, the knowledge that existence doesn't need permanence to matter. It only needs to happen once and be noticed. The story of 3i/Atlas will not end with its disappearance. Its data will ripple through scientific papers, through lectures, through future missions inspired by what it taught us. Students not yet born will study its spectrum and learn how to listen for others like it. Instruments not yet built will trace its path, measure its remnants, and refine our understanding of interstellar material. Even now, plans are forming for spacecraft that could one day intercept such visitors directly, sampling their ices before they vanish. The comet itself may be gone, but its influence is only beginning. Somewhere beyond the reach of telescopes, the object continues its silent voyage, crossing the boundary of our sun's domain. In 1,000 years, it will drift into the interstellar void once more, invisible to all but the faint glow of distant starlight on its darkened surface. Perhaps it will pass near another star someday, and another warmth will wake its frozen core. Another civilization, if one exists, might catch the same faint signal we once heard, the same whisper of hydroxyl at those same twin frequencies. They might interpret it differently, but the message will be the same. Water exists here. Life could follow. And maybe that's the quiet triumph of all this. Not the discovery itself, but the understanding that such connections are possible, that the chemistry of one star system can speak to another across the emptiness, that listening, no matter how faint the sound, can bring the universe closer to knowing itself. In the end, 3i/Atlas didn't announce anything dramatic. It didn't reveal alien messages or rewrite the laws of physics. It simply reminded us that the cosmos is full of small, perfect moments, like sunlight touching ice, like a molecule trembling just enough to sing. Its song lasted only hours, but its echo will last as long as the universe remembers how to carry light. And so, as Earth spins on, and the telescopes turn toward new horizons, that echo continues, invisible, effortless, eternal. The universe doesn't send greetings or promises. It doesn't need to. It exhales, and in that breath we find meaning. If you could close your eyes and listen beyond time, you might still hear it. A faint hum at 1665 MHz, a softer twin at 1667. Not words, not intention, just chemistry speaking softly in its sleep. And if your eyes are still open, know this: somewhere, far beyond the edge of our night, a comet is still drifting, still breathing, still carrying a trace of warmth from one sun to another. Its voice is thin, its message simple, but the meaning is vast. The universe, patient as ever, is still listening. And we, for one quiet moment in all of cosmic history, had the privilege of listening back.